Okay, so I just want to go over one of the questions of the pop quiz. By the way, test number 3 is next week, okay? Don't miss it. Right? It's only magnetism. It's a lot of conceptual questions, right hands. So bring your right hands when you're going to take the quiz, the test. And remember, if it's a negative particle, you want to use your left hand. Okay, let's look at the pop quiz. Yeah, here. So Amperes law. Just a quick review here. So Amperes law says that if you take a path, okay, so it's an invisible path, so the path is in your mind, right? And the magnetic field is a vector field. So it means everywhere in space, you're going to have a value for that magnetic field. So you're going to have a direction and a magnitude. Okay, so in 3D, that will be a vector field. So you take a path here. So every single point along the path, you're going to have like a value for the magnetic field. You're going to have a direction and you're going to have a magnitude. And then maybe you attach to that path, you're going to attach like a membrane, like a, soap film. Okay, so kind of the membrane here attached to it. And then you look at the current poking through. So it means maybe I1 is going to go into the board. Maybe you're going to have a I2 here into the board. Maybe you're going to have I3 here coming to you. Okay, so maybe it's just a current going here and it's poking through and it's going back. Okay, so in that case, it's coming this way, poking through here towards you, and then it's coming back. Let's see. Okay, so this one is into the board, towards you. Maybe you have I4. So Ampere's law says that if you sum, okay, all those little segments here, delta L, okay, times, so for every single segment here, you're going to have a value for the magnetic field. But you're going to take only the component of the magnetic field parallel to that delta L. So that will be B parallel. So that's going to be B parallel. Okay, it's going to be equals to mu 0, which is the magnetic constant, and then the sum of the current poking through. So you take your right hand, because you are going this way, which is clockwise. So clockwise. So if it's going into the board, it's going to be positive. If it's going towards you, it's going to be negative. Okay, you take your right hand. So it's going to be mu 0. So into the board is positive. I1 plus I2 minus I3. Okay, and we don't care about I4. That's how it works. Now that means, the meaning of that, because B is parallel to delta L, that means a dot product. So here you have a dot product. So this means delta L is a vector and then you dot with B. That means you are taking the component parallel to this vector. And the next step, instead of having these big segments, right, you're going to decrease the size of the segment and that will turn into, I should put something here to show that I'm go around the path. It's not an open path, it's a closed path. So that will become a closed path. So it's a line integral, but it's closed because I go around and then you go B and that will become dl. Okay, mu 0 and then the sum of the current that thread, or you can say poking through the membrane. Okay, so that's Ampere's law. It's very useful only when you have something very symmetric. So I think for the pop quiz, you're going to have something like this. Like you have some cable here, like a conductor, but the area here is square. And then here you can take another imaginary path here, it's a closed path here. So here you have a big area and here you have a small area. So you know the current flowing through here. So let's say it's current I. So through I1, you're going to have less current. It's like water flowing. Okay, if you take a cross section here, you're going to have less water flowing, obviously. So remember that the current flowing through this cross section, even though it's imaginary, okay, is 2I. So the whole flow here is to I, what A1 is to A. Okay, you remember. So if it's a square, so we did that, except in our case it was like a circle. Now it's a square. So just do uh, length times width. Okay, is that clear? So it's a review from last time. So for the pop quiz, for example, you're gonna have this one. So you can think of for a moment, like if you do this one. So they are not asking you to find a magnetic field. They're just asking you to find the line integral B ds using Amperes law. Okay, so again, for every single point along the path, you're going to have a magnetic field, but you have no idea, right, what it looks like. So it's like you are working in a vector field here in space, and then you take a path, imaginary path. Okay, so along that path, the magnetic field could be parallel to the path, it could be at an angle, it could be at a perpendicular angle. So then you have to take the parallel component. But here we don't know. Okay, we don't have. We just want to find the. We just want to apply Ampere's law. Okay, so you want to try to do this one. Okay, so the path integral. So it's a closed integral. Just apply. It goes mu 0. Okay, so you take your right hand. So it's clockwise, right? Anything in will be positive. Anything out, spreading the membrane out will be negative. Exactly. So then you will hide. This is equals to mu 0, 7 plus 5 minus 3. So this path is invisible. It's just a mathematical trick, and this is an invisible membrane, and these are poking through. So when they ask you a numerical value, you just replace mu 0, it's going to be 4 pi times 10 to the negative 7 times 2 plus 7, 9. Okay, that will be the answer. So it's B. B is Tesla, so I guess Tesla, and then that's a distance, so Tesla meters. Okay, and then you do the computation, then you will have a numerical value. Is that clear? That's how you apply Ampere's law. So, for example, if I take this one, so if I take this one, goes this way, so into it's going to be positive. So I'm going to do mu 0 times 2, right? I have to do this side. So this one here, this way, it's like in perspective. So you are doing this, going this way, it's going to be positive. So 2 is positive, 4 you don't care, 5 you don't care. Is that clear? For the upper left one, you go around the opposite directions. You go this way. So 3 will be positive, 4 will be positive, 5 will be negative, 5 will be negative. Okay, you have to take some perspective. Yes. This one upper left, go this way. 3 is positive, 4 is positive, 5 is negative, 2 is negative. So they try to trick you because you see it makes like a loop here, but you don't care what's happening there because it's not poking through the membrane. You have to attach your invisible membrane in 2D. So only the one that poking through, threading through matters. So you ignore this one, what's going on here. Just take this one in account. Okay, it's like Gauss law. Gauss law, you are taking an invisible and you are looking at the feed lines poking through the bag. It's like in the movie they say the threading. You can say poking. Is that clear? Okay, so we're good for the pop quiz. Okay, and going back to Biot and Savart. Good question last time. So that will be, so I found this one. So this one is better as a slide. So when you are trying to find the magnetic field produced by a current carrying wire, you have to divide the wire in small segments. Okay, and then you apply this equation. But you see, this is 1 over r squared. Okay, so it's an inverse square law. But one segment on its own doesn't exist. So you always have to integrate through the whole wire. When you integrate, so if you have a straight wire, when you integrate 1 over r squared, then you're going to get 1 over r. That's why the magnetic field of a straight wire, you have a dependence on 1 over r. But it's a r squared. So what's the meaning of this? This is called a unit vector. It's just to show the direction. And the magnitude is just 1. So sometimes, because if you are doing vector calculus, sometimes they want to give you r. So r is a vector position. But like the problem we did last time, instead of giving you like this point here, they're gonna give you this r here, that vector position. Okay, so r, the magnitude is obviously r, and that will be the direction, r hat. So if you are given r, and if you are asked to find the cross product, then you can change that equation here, and it becomes mu0 4 pi. Okay, so that will be I ds, so that doesn't change, cross, and now I'm going to multiply by r on top and at the bottom. So now at the top I'm going to have r hat, and then it becomes r cube. Because it depends what is given to you. If you are given the vector position, then you use that equation. If you want to use the sign, the definition of the cross product, then you can use that. But this is a vector, a unit vector, okay? Hi? I was not clear last time. So example, remember from electrostatic, if you have a charge Q, okay? So charge Q, it's gonna have an electric field that will diverge, okay? An electrostatic field always diverge, right? The drawing is not great, but imagine it's like a source. There is a source here and it's diverging. So if I want to find the electrostatic field, it's electrostatic, it's not changing with time, at a distance r, the magnitude is going to be 4 pi, I forgot, epsilon 0, q, or no, I think it's this one. Here, epsilon 0, r squared. So it's an inverse square law. But my point is that at that distance here, you see the electric field is moving away from Q. So I can define a unit vector r hat. Okay, that's just showing you the direction of the electric field at that point. So then I can write E, the electric field equals 4 pi epsilon 0 r squared r hat. Okay, it's just turning a scalar into a vector. It's just showing you the direction. Okay, Now, if you want to have a R cube, you can put a R cube, and then on top you will have a R. Okay, what else? By the way, they did launch Artemis 2 yesterday, right? And there is gravity assist, which is very cool. So it goes around the Earth because the Earth is pulling on the spacecraft. The spacecraft is pulling back on the Earth, but because the Earth is so big, it's not going to move. But the pull from the Earth is going to push it forward. So it's going to go around the Earth 2 times. I forgot. It's going to make an 8. Then goes around the moon, and then it will come back. It's called Artemis because the first program was called Apollo. And Artemis is the twin sister of Apollo. Did you know that? Right? Apollo is the god of the sun in Greek mythology, and Artemis is the hunt. She was a hunter. She has always a deer next to her. And then one day a guy killed her deer and she was very mad and she killed him. I forgot the story. But anyway, what was a tangent? Let's go back. So success was successful. And then Elon Musk is in charge of making a spacecraft that will take the astronaut from the orbit to the moon. But that's in the future. Not yet. Okay, that's what I wanted to show you. So the same Biot-Savart that you're going to apply for current carrying wire, you can apply it to a moving charge. And again, there is a R square at the denominator. And here you can put a unit vector. Okay, but the point is that if you have a moving positive charge, you're going to have a magnetic field curling around. So you use your right hand. Okay. If it's a negative charge moving, then you have a curling magnetic field, but you have to use your left hand. Okay. So we did all that, blah, 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 blah. Here it's interesting. You see the relationship 1 over R square, 1 over R square. So you can look at the symmetry between them. And these are the Maxwell equations for static, meaning not changing magnetic field and not changing electric field. An electric field that is changing with time is okay with curling. It will rotate. It can go around. A magnetic field never diverge, never converge. Okay, so we did that. This is very nice. So you can read because it's very well explained. And we've moved to next unit, unit 7. Remember, for test number 3 is just magnetism, right? Okay, so, and that will take us, I think we did this one, right? Didn't we discuss that? That's going to be on the test number 3, by the way. So it's about Michael Faraday. So 1821, Oersted. So it happened by chance. He discovered that electricity can produce magnetism. So then, of course, the question was, if magnetism can produce, can electricity can produce magnetism, then obviously you should have that. How can we produce electricity using magnetism, right? It was not that obvious because it took 10 years to discover how to do it. They took 10 years, right, to understand how to produce electricity using magnetism. So that's the way we have electricity today from the outlet. And that discovery takes you to Michael Faraday. Barely went to school just to learn to read. At the time in England, it was horrible. They were horrible with kids. Like if you are not wealthy, first of all, you will not go to school, you will go to work and you will die very young. So he was very lucky because his dad was a blacksmith, but he went to work in a library So at the time when they had book here, they had to sew them, right? To bind them together. So that's what he did. And he taught himself science. And he was very good at experiment, not at math, but at experiment. And he came up with that amazing experiment, how to produce electricity with magnetism. It's an amazing story, very interesting. He didn't go to college. At the time, if you were wealthy, you will not go to school. You had a tutor, so you were homeschooled. So anyway, you see here, that's from one of his drawing. Here had a beautiful handwriting. And what he's showing you is that if you have a loop of current, you take your right hand, okay, the loop is going clockwise, boom, that's going to be the south. In the bordered loop, that will be the north, right? We did that. If it's spinning in the opposite direction, the north is going towards you. And then he built the first motor. Okay, so that's in pop quiz 3. I think we already did something like this. See, the magnetic field goes out of the north into the south. Okay, so let's review. So that means the magnetic field lines will go up. And this is Mercury. So Mercury is a conductor. So at the time, they didn't know how bad Mercury could be. I mean, for health, it's not very healthy to play with Mercury. Thermometer used to be with Mercury, remember? So anyway, so the current goes from the power supply into the Mercury in this direction, okay, and then it goes up here through that. So it's like it can move. Okay, it's something that is hanging and it can move. So if you take your right hand, the current is going this way, and then the magnetic field is up. The magnetic field is up. So the force is in. The force is in. So you're going to have a force applied to this string or to this wire in the board. If you take your hand like this, so the current goes to the left, the magnetic field goes up, so the force will be in. So you're going to have a torque. So he built the first motor. It's called a homopolar motor. I think I don't know if I show you. If you are hands-on, you can build your own. That's what it looks like. And it's going to spin the other direction. You can try that if you like to do hands-on stuff. So it's the first motor ever built. So of course, here he doesn't use mercury. He used like electrolyte, like water with salt. That works as well. You have a neodymium magnet, and here you have a 9-volt battery. Okay, so the guy obviously was a genius, and then engineers come and build better motors, more efficient. He was more interested in the physics. Okay, so how do we generate electricity using magnetism? So first of all, you need a source for magnetism. So you need a magnetic field. It could be from a permanent magnet or it could be from an electromagnet, first. Second, you need a conductor. Okay, so in that case, you have a closed loop. Okay, it's a loop, it's a conductor, and here you have an invisible membrane. Okay, again, we will talk about that. But anyway, you need a conductor of some sort. And third, you need a relative motion between the magnet or your electromagnet and the conductor. If there is no relative motion, there won't be any electricity induced. So we're going to talk about induced EMF. Okay, so it's going to be, you're going to induce a voltage. So you're going to induce, if there is a voltage, there is an electric field. So you're going to induce an electric field. If you induce an electric field and you have a closed conductor, like a loop, then you're going to induce current. If there is an electric field induced inside a closed circuit, the electric field is going to pull on the charge, and you have induced current. So you see that in that case, the magnetic field will change with time, the electric field will change with time, and all of a sudden the electric field changes its mind. You say, listen, I'm tired to diverge or converge, now I'm okay with curling, okay, to circulate. So we'll talk about that later, but that's the main idea. So you need source for magnetism, you need a conductor, and you need some relative motion. So how we can do that? First way, you see here, you're going to have, this is a loop. So you take a magnet and you go in and away and in and away. And doing this, you're going to induce a voltage. You're going to induce electricity. So let me show you if I have. So typical example, I have a magnet, but it could be an electromagnet, right? You have the field lines going from, remember for the test, from north to south, out of the north into the south, okay? Nothing happens. But if I move in and out, you see, I'm inducing an EMF, voltage, and I'm inducing electricity. That's why electricity is so cheap. It's so easy to do. You just need an electromagnet, and then you need a loop here inside the power plant, and then that will be your load, that transformer, and then that will be your house. So very, very easy to do. So you are turning mechanical energy into electrical energy. So you need something to move, right? So we don't have someone that move in and out. It's just usually you are burning fuel, like fossil fuel or uranium, nuclear fuel, and then water turns into steam. Thank you, and the steam will make a turbine spin. Okay, so but you see there is a motion. So what is the math behind it? Okay, so I'm just going to introduce, right? Once you understand everything is just stupid math. See, so in your head, you're going to attach again an invisible membrane. So you have an invisible membrane attached to it. And you see that the field lines here are poking through the membrane. So what matters is that the number of field lines poking through the membrane, which is a surface area, has to change with time. Okay, that was the genius of Michael Faraday, because he saw, like he had a vision. He saw in his mind those field lines, and he understood that if those field lines, right, change with time as they poke through, then you're going to induce current. And then James Maxwell came, took that idea and turned that into one single equation, Faraday's law of induction. So he was a genius. So we have to introduce again the magnetic flux. Remember, the magnetic flux will be the number of lines poking through an area. Okay, so from Gauss' law, remember we have the electric flux. Okay, that was E dot the area. Okay, and we were interested by an invisible closed area. And we were looking at the number of lines poking through this area. Okay, and otherwise you have to do an integral. Okay, but now we're going to do the same thing. We're going to introduce a magnetic flux. So that will be the number of lines poking through. So now it's going to be an open area. So here I'm going to take an open area. It's just going to be B dot A. Okay, so we discussed that. We discussed how to find the flux. And the unit is Weber. So anyway, to induce current, In that case, you need to have a change in the number of field lines poking through this surface, but it's an imaginary surface. Okay? If I go really fast, I'm going to have more light because the light that I'm going to get or the induced current depends how fast the number of lines poking through is changing. Okay, so what matter is how fast those lines are poking through. I can increase the number of loops. See, more light, less light. Okay, so that's the idea. Let me show you. I have some. This one, that's the one. I think that's the one you have in Canvas, right? Yeah. So you have a conductor. Okay, it's a closed loop. So you're going to induce current. You are inducing a voltage. You are inducing an electric field. And the voltage is what? Continuous or is it alternating? Alternating current, alternating voltage, right? So the current is going to flow in one direction, opposite direction, one direction, opposite direction. So that's why we have alternating current from the outlet. It's going to go back and forth 60 times per second, so 60 hertz. We have alternating voltage and alternating current. There is no way we can do otherwise. That's why we have alternating, because something has to move at a given frequency. So there was a whole discussion at the time between Edison. There was a movie, The War of the Current, something like this, and Tesla. Tesla said this is the best way to produce electricity, and Edison said, no, we have to do direct current. And direct current doesn't work very well because you cannot transport electricity very far. To make his point, Thomas Edison was very wealthy, but he was not the nicest guy that you could find, because to convince people, he electrocuted an elephant on TV. That was a terrible thing to do, right? I don't know the name of the elephant, but you can find the YouTube video. So he electrocuted animals like a dog and an elephant just to show people, look how dangerous electricity is. Alternating electricity, it's so dangerous. So we should go direct. In the meantime, Tesla was right, but he died penniless. So I don't know what destiny has done for me. Not sure. Here, it's a very nice video.
When you connect the coil on the supply, it starts converting electric energy into magnetic field. Now let's take a different case. When a magnet is suddenly put near to the coil, an EMF is rising at the end of the coil. But this EMF will disappear as our magnet stops moving. If we pull magnet in opposite direction, EMF will also start producing in opposite direction.
So even though you are not closing the loop, so here you cannot induce current because the current cannot flow, right? But you are still inducing an EMF. You are still inducing a voltage. And sometimes in engineering, they will say you are inducing a voltage because the lines here are cutting through the loops. I say because the number of loop lines here increases and decreases, poking through the membrane. They say because the lines here are cutting through the loops. That's when you're going to have induced voltage.
Producing EMF keep our magnet. It is called electromagnetic induction. This phenomenon is used in countless applications.
Now you have an induced current. So you see, even though you don't connect to a load, you're still going to induce EMF, induce electric field. Now, if you connect it to a load, now you close the path. So then you're going to have an induced current, which will be the induced EMF divided by the resistance. What it's called? Video, electromagnetic induction. here.
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to Faraday performed. So I have an ammeter here, a magnet, and two coils. This coil has 100 turns, and this coil has 25 turns. I will first connect the 100 turn coil to the ammeter. And I'm now going to take the magnet, and notice as I move it towards the coil, I get a pulse of current in the positive direction, and when I pull it out, there's a pulse in the minus direction. And notice if I just hold the magnet there, there's no current flow. It's only when the magnet's moving, when there's therefore a change in magnetic flux with respect to time inside the coil. If I move the magnet slowly, I get a small current. And if I quickly, I get a larger current. Okay, so it's the rate of change of magnetic flux inside the coil that determines how much current is flowing. And we see that I can get about 10 microamps if I try to move the
We did
magnet.
that in the lab.
Yeah, we had to move the magnet in and out of several different solenoid coils
Right.
to measure the deflection.
Good. So it makes easier to understand. Okay, let's see. Okay, so again, in and out here, you see it's alternating current. So how I can increase the current here, I can increase what else? What can I do? I increase the area. Okay, so by increasing the area, you're going to increase the number of field lines poking through or cutting through. So that will work. I can increase the number of loops. Okay, so that works also, right? It's going to be brighter, so more current induced. If I want to increase the number of lines, remember the lines is just a way to visualize. So if you have more lines, it just means that your magnet is stronger. That means the magnet is producing a stronger magnetic field. Okay, the field lines, it's just a way to visualize, to show, to draw. Okay, so if you have a lot of lines, that means stronger magnetic field. So if I have a stronger magnetic field here, if I increase the strength of the magnet, I'm going to increase the number of lines. If I increase the number of lines, I'm going to increase the light. Okay, so you can increase the area, you can increase the number of lines, and you can increase the magnet. Doing so, you're going to increase the number of field lines poking through. The loops, it's like adding up. Okay, you add up. So if you have 4 loops, you're going to have 4 times the voltage induced. Are you with me? So magnetic flux, okay, it's like the electric flux. It's going to be the magnetic field times the area times the cosine, remember, between the magnetic field and the normal vector perpendicular to the area. So if you want to induce a voltage, you can change the magnetic field. You can change the area, okay, because if you make the area smaller, you're going to have less magnetic field lines poking through. Or this is the way we do it to generate electricity. We spin. Okay, if you spin, you see the number of field lines poking through is going to change. You are changing the orientation between the magnetic field and the area. Okay, we spin at a rate of 60 cycles per second. And then you have something called, we get back to that, motional EMF. It means that if you have here a conductor, so it's not closed, so you cannot induce current. Okay, so we can review for test number 3 to make sure everyone is fine. But you see, you have a conductor. In this conductor could be a piece of copper. Agree? Okay, so if it's copper, the charge carriers are electrons. And then you move that piece of copper inside the magnetic field. The magnetic field is going into the board. So I'm using my left hand because these are electrons. Okay, so you see what's going to happen. The electrons are moved, okay, because they are part of the conductor. There are free electrons on the conduction band. So you're moving the electron. The magnetic field goes into the board, so the force will be down. Very good, right? So here you're going to have a minus, and here you're going to have a plus. If you have a plus and you have a minus, that means you have a voltage, a potential difference. So you are also inducing voltage. So all this means that you are transferring energy from mechanical energy to electrical energy. And the magnetic field is the way to transfer energy. But you need to have conservation of energy. Okay? So again, you imagine a membrane attached to your conductor, and you are looking at the field lines poking through. And what matters is how fast the number of field lines poking through will change. Okay, you can change the area, that will work. Okay, so that will be the equation, and we'll get back to that. Okay, so that means the EMF so the EMF induced, so this is voltage, will be the number of loops d phi over dt. That's called the magnetic flux. Okay, so the magnetic flux, it's going to be B, the magnetic field, times the area. So I'm just, it's magnitude, right? It's a dot product. So it's going to be what? B times A. Yeah. But the Gauss law, it's a closed surface. Here it's a membrane, so it's an open surface. So it's going to be A times B, and here you have the cosine between the area and B. Okay, so I'm not going to explain why, because we already talked about flux. And yeah. Okay, so that will be Faraday law. Faraday's law of induction. Okay, we're going to take example. So in that case, you see only the magnetic field is changing. So that equation will become number of loops times the area poking through times the rate at which the magnetic field is changing. If you are changing the area, then only the area is changing, or you can change the angle. Is that clear? Okay, let me make it clear, and then we'll take example. But go back to the first unit to remember what's a flux. Okay, so flux, it's got the dot product between B and A. A, in that case, it's going to be an open surface. And so you can have a vector here, A, and that will be your area A. So the area has an orientation, right? It's like an area like this. This is an area, and you need to attach a vector to it, perpendicular to the area, to show you which way is the orientation of the area. So anyway, just bear with me, and then we take example. So the magnetic flux is the magnetic field times the area times the cosine theta, and theta is the angle between B and A. So I have another slide, but if the magnetic field is going this way, that's going to be your angle theta. Okay, so the EMF is going to be the number of loops times d phi over dt. Okay, So it's going to be d and then a b cosine theta over dt. Do you agree? By definition. And then something has to change. It could be the area, it could be the magnetic field, or it could be the angle. Okay? If it's the area that is changing, you can factor out b and cosine. If it's b that is changing, you can factor out a and the cosine, or it could be spinning. So we're going to take some example, but this is the ideas. I forgot to show you. There is one video, just the beginning. So you have the field lines, right? Stronger magnet, more field lines. So now you have a conductor, it's a loop. So imagine that you have a membrane here attached to it. So that's one way to understand what's going on, right? So as you move the conductor up, the velocity is this way, magnetic field is this way, so the force will be there. So the electrons are forced to move. So you are inducing current. That's just one way to understand what's going on. So you see, you have your conductor, you attach this invisible membrane, and as long as that the number of field lines poking through is changing, you're going to induce a EMF, you're going to induce a current. The number of field lines poking through is called the magnetic flux, okay, which depends on the strength of the magnetic field, it depends on the area, and it depends on the orientation, right? If this is your area and the magnetic field goes that way, you have no lines poking through. Okay, maximum will be perpendicular.
The current flows one way. Decrease.
Oh, that's another example. So here you have an electromagnet and you turn on and off, right? So it's connected to a power supply. You turn on the power supply, turn off. So the magnetic field will expand, collapse, expand, collapse. So the number of field lines poking through this invisible membrane is changing with time. So you are inducing voltage, you are inducing current, right? You are poking through. Now, if that's how we create electricity in a power plant, so you're going to have a conductor here, it's called the rotor, and it's going to spin. You make it spin because it's attached to a turbine. It's going to spin at a rate of 60 cycles per second. You have a magnetic field here, and you see that the magnetic field lines, the number of magnetic field lines is changing with time. So do you have any field lines poking through here? No, 0, right? So it goes from 0 to maximum, and then it's going to be negative, then 0 again.
Constant magnetic field continually changes the flux through the loop. The resulting voltage and current are sinusoidal, going first one way, then the other.
Isn't that cool? So this simulation is very nice because this is a AC generator. That's how it works. And you see here, this vector is just the vector area because it shows you the orientation of the area. So the EMF that you're gonna induce here is gonna follow a sine wave. That's what we get from the outlet. Okay. So again, this is called a magnetic flux. Magnetic flux depends on magnetic field because if you increase the strength of the magnetic field, you increase the lines. Okay, so you're going to increase the number of lines poking through the area. If you increase the area, obviously you're going to catch more field lines, so the flux is going to increase, and it depends also on the orientation between the magnetic field and that vector, okay, the vector perpendicular to the area. Okay, so if those vectors are perpendicular to each other, cosine 90 is 0, there is no field lines poking through. If they are parallel to each other, that's going to be cosine 0, that will be the maximum. If they are opposite to each other, it's going to be negative. Now, if they make an angle with each other here, then that means the flux will be, you multiply by the cosine of this angle here. Is that clear? And again, that will be Faraday's law of induction. The EMF induced is the number of loops times the rate at which the flux is changing. So the number of field lines poking through changing with time. Okay, so that's called Faraday's law of induction. So you could also change the area. So if you change the area, that will work because again, you see the field lines here are going into the port, and if you squeeze it, then you have less field lines poking through, but it has to change. Okay, so changing has to change with time. So this is called electromagnetic induction. Okay, so I want to introduce something called Lenz law, Lenz, because there is no free lunch. Okay, energy is always conserved. So that will be very important for all the pop quizzes and conceptual questions coming up. So you come in toward. Okay, so the number of field lines poking through that invisible membrane attached to the loop, it's going to increase. Do you agree? Do you agree? And you're going to induce a current. So the question is which direction the current is going to flow. But because there is no free lunch, you see, you are converting mechanical energy to electrical energy. So you have to feel the pain. No pain, no gain. So it means that you have to, as you go in, you have to do work. You have to push. It has to be hard. You really have to push really hard. And why is that? That it's going to be hard because the current is going to flow in the direction to oppose you. So it's like, no, you don't. You're coming in, and that electromagnet is going to turn into a magnet that says, no, you don't. It has to be hard. Okay? Otherwise, you cannot convert energy. It doesn't work. There has to be conservation of energy. So you take your right hand, and because north is coming toward the solenoid, then the current has to flow this way. Do you see why? If it's flowing this way, that will be north. North and north will repel, right? So you have to feel the pain. It has to be because the electromagnet here or the loop says, no, you don't. I don't like you. Go away. I hate you. And as you move away, it's going to be the opposite. Now it's going to say, no, I changed my mind. Now I like you, right? No, you don't. Stay with me. So now the current is going to flow in the opposite direction because south and north attract. So I don't know if you know the opera Bizet, right? Bizet, like if you don't love me, I love you, but if you love me, I hate you. It's Stromae took that same song, right? So anyway, it's the no, you don't. Okay, you have to feel the pain because of conservation of energy. No pain, no gain. Okay, so this is here. You can see that here. As you come in, it says no, you don't. It's repelling. Right, coming in, it's repelling. You see? So that's why in the equation you're going to have a negative sign. So typical, it's going to be conceptually challenging if you don't understand. But if you understand, it's going to be easy. So it's called Lenz law. No, you don't. So if you come in, it's going to repel. If you move away, the number of lines decreases, so it's going to attract. You see? Because of conservation of energy. Okay, induction experiment, it doesn't have to be done with a magnet. It could be done with an electromagnet, or for example, you can open or close a circuit. So if you close a circuit, the magnetic field will expand. If you open a circuit, it will collapse. So in both cases, the number of field lines will change, and you're going to induce a current or induce voltage, right? A magnetic field that will be produced here by the coil doesn't happen instantaneously. It takes time for the magnetic field to expand, and it takes time to collapse. That's why it could be dangerous sometimes if you have a closed circuit and there is a coil. You always have coils. You have stray coils, like even a wire. You can think of it as a coil. So if you're listening to music and you unplug, right? So what's going to happen is that the magnetic field will collapse. You're going to induce electricity, and the appliance will work on its own before it's going to turn off. So you have to be careful, because if you open it here, you can have a spark. Because the magnetic field will collapse, you're going to induce a voltage in the circuit that you open, and you can have a spark. It's like the old car, the spark plug will work this way. See, a magnetic field doesn't happen instantaneously, right? So you open a circuit, so the magnetic field collapses, so the number of field lines will decrease. A magnetic field will expand, but it takes time. So the number of field lines increases with time. Okay, I don't know what I'm talking about. I forgot. Okay, here. Okay, let's try to do that. This one comes from my algebra-based class, so it should be easy. Okay, you just apply the equation. Yeah. So you can help each other, talk to each other, blah blah blah. Okay, so what's the equation? So the EMF, there is a negative sign because of Lenz law. No, you don't. But I'm going to forget about it, right? I'm just writing without negative sign. The number of loops, d phi over dt. And phi is the magnetic flux. It's going to be B, the magnetic field, times the area, times the cosine theta, and theta is the angle between B and the area. Okay, so if you have an area this way, and you have a magnetic field that way, that's going to be theta here. And you have a membrane, invisible membrane here. Okay? So do it. I'm taking my time. So if B changes, then EMF will be the number of loops. I can factor out A, doesn't change, cosine theta, and that will be left here. dB over dt. Do you agree? Okay, when you take the derivative, A does not change, cosine does not change. If it's the area that changes, yeah, it's perpendicular. So it's going to be N B cosine theta d. Okay, and then next we'll see when it's the angle that will change if it's spinning. But now I think it's just going to be case number 1. Okay, so that will be the number of turns. That's the area that does not change. Magnitude, so B1 and then B2. So it's not even a derivative here, right? It's just a delta because it's for algebra. And here you have the time elapsed. Right? So I'm just going to write EMF equals number delta. It's a delta. I can make it even clear as much as I can. And you see, only B is changing. So it's going to be the number of loops, the area, cosine theta, delta B over delta T. And this is equals to 1. Because it says it's perpendicular. So that means that the angle here is 0. Perpendicular means this. Yeah. Perpendicular to the area. Okay, so that means this angle here is 0. Okay? So the EMF, I didn't do it, okay? So you do it. Number of loops times the area, so 0.0015 times final, so 0.06 minus 0.05 over the time elapsed. You get that? So what do you get? EMF is 0.003 volt, which is 1, 2, 3, so 3 millivolt. So you are inducing a voltage. If there is a voltage, there is an electric field. And what is the electric field doing? It's circulating. It's going around. Okay, it's changed its mind. It's not diverging. It's not converging. It's going around. Okay, we can even say it's a circulating EMF. You cannot say it's between this point and that point. It's just just induced, and it's circulating. Yeah.
Why didn't we use the negative sign?
Oh, because the negative sign is here to remind you of Lenz law. So negative sign means be careful that you have to use Lenz law to find the direction of the current. But it just says that if it's increasing, it's going to flow in one direction. If decreasing, it's going to flow in the opposite direction. Okay. But when I don't use the negative sign, it just means I'm worried about the magnitude. I'm just focusing on the magnitude. And the yes, and the negative sign here is just to tell you which way it's going to circulate. So negative means no, you don't. So in that case, you see, you come toward the loop. Okay, so the loop says no, you don't. So the current is going to flow in this direction here, because then it's going to be pushed away. No, you don't. No free lunch, okay? No pain, no gain. That's the meaning of the negative sign.
Thank you.
Okay, so try to do this one. So in that case, okay, it's the magnetic field that is changing. The magnetic field is going into the board. What's happening with time? Maybe you take your magnet and you go in the board, or your electromagnet and you go in the board. So with time, the number of field lines poking through the membrane is increasing with time. So that means you see, with time, you're going to have more of those magnetic field lines poking through. It's going to increase. Okay, so what is given? We see that dB over dt is 0.1 Tesla per second. So you have to look at the unit. Tesla per second means it's a rate. Okay, it's not just a magnetic field, it's a rate. There is a time. Okay, what else do we know? The area we know, right? It's going to be pi r squared. Perpendicular, so theta equals 0. So we can find the EMF induced. Okay, so it's going to be the number of loop. The area does not change. The angle does not change. It's going to be dB over dt. Okay, so it's going to be number of loop is 1 times the area times 0.1. That's going to be the EMF. Yes? Which is 3 millivolts. You get that? Hmm? Okay. Yes? Okay. And then it's a conductor, so any wire has a resistance R. Okay, so I can use Ohm's law to find the current induced. So it's going to be the EMF times the resistance. So it's going to be 0.03, 123 divided by 2. Oh, you can say that. You can keep the milli. You can keep the milli, so that way you're going to have 1.5 milliamps. Okay? Any question? So pay attention because that's going to be a lot of conceptual questions for this part as well because of no, you don't. So you see the field lines are going into the ball. Into the ball. So the current says, no, you don't. No, you don't. So the current is going to flow this way, which is counterclockwise. So the magnetic field produced by the current, you remember it's a second hand, the second right hand rule. If the current is flowing this way, the magnetic field goes that way. So the current is going to flow this way to say, no, you don't. I don't like you, right? You want to go this way? No, you don't. Right? So that way, whoever is pushing the magnet in has to do work. Okay, so the current will flow counterclockwise because the magnetic field induced will say, no, you don't. If the magnetic field decreases, so it means if you move away, the current will flow the opposite direction, clockwise, and they say, no, you don't. Okay, so if you like me, I don't like you. If you don't like me, I like you. It's the Carmen, you know. L'enfant est amour de poème. Okay, so counterclockwise. No, you don't. Okay, so for example, so here are some examples. So in that case, what is, so you already have d phi over dt. If you divide the number of loops by 2, what's going to happen to the EMF? Right, you already have d phi over dt, so you already have the EMF. If you decrease by a factor of 2, so okay, let's make it clear. So you have this, right? So the EMF, it's going to be the number of loops, the change of B times A delta T. So it's going to be the number of loops times 4. So if you have 4 loops, the EMF induced will be what? 4 times 4 is 16 volt. If you have only 2 loops, it's going to be 4? No, but you already have 4 here. So if N 2 times 4 is 8 volt. Right? It's just to show you that it depends on the number of loops. So in that case, you see if I go here, you see if I decrease the number of loops, divide by 2, the induced EMF will be also divided by 2. So 16 and 6 volts. In that case here, okay, so this you have to pay attention. What matters is the area through which the magnetic field lines are poking through. So in that case here, at a given time, that will be this area. As long as there is a change, there will be an induced EMF. If there is a change in the area through which the lines are poking through. So once so it's moving, right? It's moving here. Once it's there, is there an EMF? Is there an EMF induced? Is magnetic field is changing? No. Is the area through which the field lines are poking through is changing? No. So is there an EMF induced? No. Only when it's getting inside and only when it's leaving. Because something has to change. Here the area does not change, the magnetic field does not change, the number of loops does not change, no induced EMF. only when it's getting in and getting out, there will be a EMF induced. Okay, so in that case, the EMF will be number of loops is 3. Okay, magnetic field does not change, is 0.2 times the area at which, the rate at which the area is changing, so times 0.2, which is 0.12 volt. But if it's inside here, there is no change. The area, when we say the area change, is the area through which the membrane, right? So the area through which the number of lines are poking through. That's how it works. Okay, number 3. What's happening here? Okay. A storm. I thought there's not supposed to rain today. Hey. So what do you think? Hello. So the number of lines poking through increases. So it's just the number of loops, right? Area does not change times the rate at which magnetic field is changing, right? So it's going to be 5 times 0.002 times 0.4 volt. Be mindful of no you don't. Okay, you coming in, the current is going to flow in this direction because it says no you don't. If you move away, the current is going to flow in the opposite direction and say no, I like you, okay, come back. So that's why it's flowing in this direction. Okay, finally, so that's interesting because one way to look at it, when the angle, so in that case, the angle is changing, right? Because that's an AC generator. So you have a loop here and it's spinning. Because it's spinning, this angle here, that angle here, okay, it's going to change with time. It's going to be omega t. Right? Omega will be the number of cycles per second. Okay, so 2 pi is 1 cycle. And that will be the time for 1 cycle. So omega is just revolution per minute, except the unit is in rad per second, right? 2 pi rad is just 1 cycle. So it's spinning at a constant rate. So one way to look at it, we're going to say, and that's an AC generator, we're going to say that will be the number of loop, delta. Okay, you're going to have B times the area times the cosine omega t, okay, over delta t. Okay, so I'm introducing the AC generator. So when you take the derivative, it's going to be number of loops, B, times the area, omega, and here you're going to have a sine omega t. So that's why the voltage that we get from the outlet is following a sine function. Okay. But here they do it a different way. They're going to say it's the area that is changing because look, here, so this is the area A, and here you have, you can think of that as the effective area. Okay, so when you write the flux, you can say it's B dot A, which is B, and then A, the area perpendicular to B, because the number of field lines here depends on this area there. Okay, so you can write it this way. So then the EMF will be the number of loop, and then B, and then D over dt. That just it means. It's just a different way to look at it. But that's what we're going to do. But they just do it a different way. They look at this area that will change with time. Think about it. It's called the effective area. Think about it. So the number of turns is 20. The magnetic field is 0.2. And then you have 0.2 here. Are we good? Right? So again, magnetic, so that will be the electric flux, but the same thing for a magnetic flux, right? The flux is the number of field lines poking through. In that case, it's an open area. With Gauss law, it was a closed area. Okay, so in that case, the number of field lines will be equals, you see the number of lines poking through this projection of the area, A perpendicular. So A perpendicular is just A times cosine theta. Okay, you will get the same thing. Either you can say AB cosine theta or B times the perpendicular here to B. And here the flux equals 0. Okay? Just to explain, this is more like math, geometry. Okay, do that. This one is easy. Go, 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 go. Easy, 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 easy. So it's a closed loop. So it's a conductor. Magnetic field is going into the board. So maybe it's increasing. I don't know. It's maybe you take your magnet, you go this way. So the number of field lines is increasing with time. So you're going to induce an EMF, an induced current. And let there be light. Yay! So this unit is, once you understand the concept, you know, it's just math. Oop, 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 oop. Okay, so EMF is going to be the number of field lines. The area doesn't change. And then we just have delta B over delta T. And the angle is 0 degrees. So cosine theta equals 1. So we don't have to worry about it. Okay? So the induced EMF, you need 3 volts. So you need to induce 3 volts equals number of loop is 1. The area is going to be diameter is 20, so it's going to be 10, so it's going to be 0.1 times pi times, we want that. That's what we want. So what did you get? So it's going to be 3 divided by 0.1 square divided by pi. 9.5 or 95.5? Yeah, 95.5 Tesla per second. Okay, which way is going to flow? Clockwise or counterclockwise? If it's increasing, it says no, you don't. So into the board, increasing, and it says no, you don't. So is the current going clockwise or counterclockwise? No, you don't.
Yeah.
Yes.
It goes in the opposite
Yes.
direction of what's going into the hole.
Exactly.
Going down.
Counterclockwise. Counterclockwise, no, you don't. Okay? Make sure to open your textbook, right? And maybe we leave that for next time. Okay, you can do these are easy, so you can practice for next time. So Lenz law, again, you coming in? No, you don't. It's going to flow in this direction. You want to move away? No, you don't. Now I like you. Okay, I don't like you. Now I like you. Okay, so this one is north, north, and north repel. No, you don't. And then you want to move away. No, you don't. Right? It's Carmen. Same story. That's why you have a negative sign. Okay, it's Lenz law. Because the induced voltage or current is to oppose the change giving rise to the induced effect. Because of conservation of energy, you have to feel the pain. Okay? There's a saying, you create your own monster. I don't know if you know the story about Frankenstein, the real story about Frankenstein. There is a very funny movie called Frankenstein Jr. with Mel Brooks, but the real story of Frankenstein, he creates his own monster that will, at the end, ruin his life, right? So same thing here, you create your own monsters. That's what they told me about my kids. You create your own monsters, right? Just kidding.